Yeah, welcome to VLSI Simplified YouTube channel. As a part of 30 days Verilog lecture series, today I'm going to explain Verilog RTL code for ring counter and Johnson counter. So those are the special counters. By using shift registers, we can design those counters. Okay. First, I will explain you. We are in day 13. First, I will explain you about the ring counter. Okay. So if you see the ring counter, this is the first I will execute in EDA playground. So first I'll go with ring counter. This is my ring counter. Uh, so if you go to this code, module ring counter. So you need to declare the input. Input clock with y data type and input y reset n. Reset n is asynchronous active low reset. Okay, this is asynchronous active low reset and output range 3 down to 0 out. Okay, this is 4-bit output count. Okay, and sequential logic I need to use always at the rate passage of clock or negate of reset and reset n. Okay, this is asynchronous active low reset. Okay, begin if not of reset, if reset equal to 0, so this is the initial value for the ring counter 0001. Okay, so preset the counter to start with single high bit. So this is the LSB bit is one, remaining all are given to the clear signal. Okay, so normally there are four flip-flops will be there. Last flip-flop is given to the preset signal and remaining three flip-flops are given to the clear signal. So what happening? That means preset and clear, as you know, those are asynchronous inputs. Irrespective of clock, it will force when preset is activated. Irrespective of clock, it will force the output to 1. When clear is activated, it will force the output to 0. Okay, and else begin. So shift left and circulate the MSB to LSB. Okay. So here we need to shift left. Okay. This is shift left operation. And whatever the MSB is there, that is coming to the LSB position. Okay. Out 2 down to 0, out of 3. Okay. Out is non-blocking with out 2 down to 0, out of 3 end and this end and end model. Okay. This is the code. And coming to the test bench. So if you see the test bench, so module TB ring counter. This is my module name of the test bench. I need to declare the test bench signals, reg clock, reg reset n, and wire 3 down to 0 out. Okay, I need to instantiate the DUT in the test bench. How to instantiate? Design name followed by the instance name and dot clock clock. Okay, dot reset reset dot out out. So the variables outside the bracket are design inputs and outputs. Variable inside the bracket are test bench variables. Okay. Next clock generation. Always hash 5 clock equal to not off clock. So I'm generating the clock. That means this is off for 5 nanoseconds and this is on for 5 nanoseconds. Total clock period is 10 nanoseconds with a clock frequency of how much? 100 megahertz. Okay. And I need to give the stimulus to the block. Okay. Initialize the inputs. First I am initializing clock equal to 0 and reset n is equal to 0. As this is asynchronous active low reset, no. So active low reset means when reset equal to 0, so reset is asserted. Assert the reset at time t equal to 0. Okay. And I want to monitor the signals. For this, I am using $monitor system task, time equal to percentage t, reset equal to percentage b, and the counter out equal to percentage b, comma, dollar time, reset in and out. Okay. And hold for 2 clock cycles. Okay. Then release the reset. Okay. So ash 20. So hold for 2 clock cycles and release the reset. After that, I want to run these signals for 100 time minutes. Okay. Observe these multiple full ring cycle and after that terminate the simulation. For this dollar finish I can use. And these are the VCD dump block required for EDA playground for EP visualizer. Okay. So what are the instructions we are using? Initial begin, dollar dump file, dump.vcd, dollar dump vars 0, comma, TB underscore ring underscore counters. Okay. So this is the code for ring counter. So if I execute in EDA playground, so open the EDA playground and log in with your mail ID. Go to this RTL file right click, select all, copy, and go here and paste. Right side we need to paste the design. You need to write the design. Left side you need to write the test bench. Okay, test bench file also. Copy this and here we need to paste and go to tools and simulator. Select Aldec Rivera and open EP waveform after run and save, run. So you get the waveform 1, next 1 0. Okay, actually 0 0 1 only. Again 0 0 1 0 0 1 double 0 1 double 0. Again 0. So 0 it is not showing. Okay, okay, in this waveform 0 it is not showing. And here also. So that means this is the 4 bits now. So 4 bits means you can see here. So this is what 0 0 0 1. Okay, 0 0 0 1. And next in this cycle 0 0 0 0 0 1 0 and 0 1 double 0 and 1 double 0. Okay, like this we will get again it will start. Okay, it's like a ring. Okay, and so 0 0 0 1 0 0 1 0 0 1 double 0, again it will come to 1 double 0. Okay, like that it will repeat. Okay, you can see in the log file also. See here. So here you see. So 0 0 0 1 and next here after 10 time it's 0 0 1 0. Okay, this is actually when reset is activated. Okay, when reset is activated, so it will come to the initial state as this is active low reset now. So when reset equal to 0, reset is activated, it will come. So what is the initial value? Counter output is 0 0 0 1. Okay, after 20 time minutes, what happens? Reset is resetted and it comes to 0 0 0 1 and next 25 time minutes 0 0 1 0, again 35 time minutes 0 0 0 1 double 0, again 45 time minutes 1 double 0. Okay, like that it will repeat. Again it will come to the initial state. At fourth clock cycle, it will come to the initial state. So that's why for the ring counter, it's a modern counter. Okay, for 4 bits, you are getting mod 4. 4 bit ring counter, you are getting mod 4. So, what is the mod of the ring counter? Means modern. Suppose if you are giving using 8 flip flops, you will get mod 8. After 8 clock pulses, it will repeat the same sequence. Okay, so this code I can use in the EDA playground also. First, go to this project, new project. Next, and let us take, I'm giving the project name. Let us take, we are in which project? Day 13, no? So day 13, I'm giving the project name as, let us take special counters. Okay, special underscore counters, special underscore counters. And go to file where I want to store this code. Okay. Um, so I want to store in, mm, so where I want to store training and development and next need to go to VLSI material 30 days 30 days we are in day 13, no? Okay, day 13 and so I will selecting this path. Okay, so this special counter will be stored in this path. Okay, next RTL code and create the file name, give the module name only. Okay, so this is my module name. Okay, copy this, choose the location. I gave the special counters, no? So this one, select this folder. Okay, next, and next, and finish. Okay, module name is okay. Okay, okay. This is a ring counter. So here this code I'm copying and here I'm pasting over here. Save and go to simulation. Add the simulation. Next, create the simulation. Okay, give the module name only. What is my module name? TB underscore ring counter. Okay, copy this and paste. Choose the location, special counter, select OK, finish. And module name is also same. I'm giving same as module name. Okay, here my simulation file is created, test bench file. Okay, and go to this test bench file, select all, copy and paste, save. Okay, so my design is instantiated in the test bench. Okay, so ring underscore counter. Okay, so here if you want to see the elaborated design, go to RTL analysis, open the elaborated design. Okay, so we want to see the how the tool is converted your code into gate level netlist in terms of hardware. Okay, so it's reading the netlist. It will take some time. Yeah, like this. Tool is converted my code into gate level netlist. See here, preset is there. Okay, so for last flip flop will be given to the preset, and the remaining flip flops are given to the clear. Okay, and this is actually we are designing with a D flip flop. Okay, so D flip flop and the Q bar is connected as a D input like this. We are designing clock will be there. Okay, and coming to the simulation, run behavioral simulation. So you can see in the log file also. So see here, initially when reset equal to 0, this is the initial count value. And when reset is deasserted, so this is the initial count value. And after this count will come to 0010, 0100, again 100. Okay. Again it will start 0001. At fourth clock cycle, it will come to the initial state. Okay. So you can see in the this also fit to page. Now you see. So here right click, so here go to radix binary. So when the reset is activated, okay, when the reset is activated, what is happening? That means all the outputs will be coming to the initial state. What is the initial value of ring counter? 0001. Okay, here the reset is activated. Reset is 0. Asynchronous active low reset. Okay, and here reset is deasserted during this passage. Okay, it is counting. It is going from which counter? 0010. Why? Because as Q is connected as a feedback to the D input, no. So that 0 will come and that will be feedback. You are getting 0010. Okay, just to go through the concept of ring counter in digital, then you can understand this 0100 and 100. Okay, again here at the fourth clock cycle it will repeat. It's the sequence. Okay, now it becomes whatever the initial state is there, 0001, it is coming to the same state. Okay, again it will repeat. Okay, 0001, 0010, 0100, again 100, again it will at the eighth clock cycle it will come to the initial state. Okay, so like this we can see in the um, Xilinx Vivado. Okay, at the time being, I'm explaining in EDA Playground and Vivado only. So if you want the course, just give in the comment box. I will share the codes. Okay, give your just if you give your mail ID or details like this, I will share the codes in the to you. Okay, and next I'm going for the Johnson counter. Okay, so what is the other name for Johnson counter? Twisted ring counter. We call it the twisted ring counter. That is the Johnson counter. So this is the Johnson counter. So the difference between a ring counter and Johnson counter is for the Johnson counter, Q bar is acting as a feedback to the first flip flop. Okay, that is the only. So for the ring counter, Q is acting as the feedback to first flip flop, and for the Johnson counter, Q bar is acting as a feedback for the uh, first flip flop. Okay, so here when it will repeat its sequence means after this is a 4-bit. No, 4-bit means after 8 clock pulses it will repeat its same sequence. That's why this is if for 4-bit Johnson counter mod is 8. For n-bit Johnson counter mod is 2n. Okay, that you need to remember. For ring counter, n is the mod n is the mod of ring counter. Okay, n is the mod of the ring counter. For Johnson counter, 2n is the mod of the ring counter. Or sorry, Johnson counter. Okay, so if number of bits are 4, after 8 clock pulses, it will repeat its position. Okay, that we'll see in the simulation. So this is the code related to the Johnson counter. Module Johnson underscore counter. I need to declare input clock, input reset, output 3 down to 0 Q. And I'm declaring one temporary register that is 4-bit Q underscore register. Always at the rate passage of clock or passage of reset. This is active high reset. Begin if reset. If reset equal to 1, I'm initializing Q register equal to what? 4 tick binary, all zeros. Else I'm using concatenation operation. So Q underscore register equal to what? Q underscore register 2 down to 0, comma, not of Q underscore register of 3. Okay. And after that, whatever the value you got in Q underscore register, that I'm using a continuous assignment statement assign. Okay. So that's why I'm using after the means after completing the procedural block only, I'm using this Q. That's why I need to use continuous assignment statement. Q I declared with void data type. No. So Q equal to Q underscore reg. I'm assigning. Okay. End module. Okay. This is the Johnson counter. And coming to the test bench. So here if you see the test bench module Johnson counter underscore TB. So as the test bench doesn't have the inputs and outputs, only variables will be there. I need to declare the variables. Reg clock, reg reset, wire 3 down to 0 Q. I need to instantiate my design in the test bench. How to instantiate? Johnson underscore counter, instance name, DUT, dot clock, dot reset, dot Q. Okay. So the variables outside the bracket are design inputs and outputs. The variable inside the bracket are test bench variables. And I need to generate the clock. For generation of clock, initial begin, clock equal to 0, forever, hash 5, clock equal to not of clock. Okay. So I'm generating the clock with 10 nanoseconds period and 100 megahertz frequency. Okay. Initial begin. So these are the two instructions I want to execute in EDA playground. Dollar dump file Johnson underscore counter dot VCD. Dollar dump var 0 comma Johnson counter underscore TB. Okay. As this is asynchronous active high reset, no, first I need to apply the reset. I need to wait for 12 time minutes. After that, I'm resetting the reset. I need to check for that means total time cycle. That is 120 time minutes. I need to check. Dollar finish for terminating the simulation. End. And if there any change in the variables like time, reset, and queue, dollar monitor we need to use. Dollar monitor end and end module. Okay. So this is how we need to write the test bench. Okay. So first I am executing in the EDA playground. Okay, this one. So go to new file. Go to new file. So here ring counter I will close. Yeah, we are in Johnson counter now. So select all. Copy this code and go to the EDA playground. Here we need to write the design. Right side and left side we need to write the test bench. Right click. Okay. Copy. The difference between the test bench for all the sequential circuits are same only. and all the combinational circuits are same only. So for the combinational circuit, you have four steps are there. Okay, initializing the edge variables and initialization, and next initialize initializing the variables of the test bench, initialization of variables, and giving the stimulus. Okay, for the sequential circuits, one more step will be added. So initializing the variables of the test bench, instantiation, and generation of clock will be added. And the initialization of edge variables and generation of clock and giving the stimulus. Okay, so five steps will be there. Five steps you need to remember for sequential circuits. Four steps you need to remember for combination circuit. But test bench is same only. Okay, so that steps you need to remember for writing the test bench. Okay, and next, yeah. So select all, copy, and one second. Yeah, here I'm writing the test bench. Go to tools and simulators, Aldec Rivera. Use the EP from after run. Run this. Yeah, see here. So that means initially this is 0 only. Okay, this is 0 only. Again 0 0 0 1. Why? Because Q bar is connected as a feedback, no? So you'll get a 0 0 0 1, and next 0 0 1 1, 0 1 1 1, and next 1 1 1 1. Okay. After next cycle, what happens? As Q becomes 1, Q bar becomes 0, no? Again 0 will come. So here you have triple 1 0, again double 1 double 0, and 1 triple 0, again 0 0 0. 88th clock cycle, see here 80. 80 means what? 88th clock cycle, it is coming to the initial state. So that means I can say that so 2 into number of bits. Okay, 4 bits, 2 into 8. So in general, for n-bit Johnson counter, so what is the mod of the Johnson counter? 2n. Okay, that you need to remember. So it's one important question. They will ask in the interview, what is the mod of ring counter? What is the mod of Johnson counter? Why that much mod? Why? Because during that clock cycle, it will repeat its same position. Okay, so that is this. And in the log file also, I can see here. So when reset is activated, initially the output will be 0 only, and so first cycle 0 0 0 1, this is initial value. 0 0 0 1 0 1 1, and next 0 triple 1 and 1 1 1, triple 1 0 1 1 0 0 1 0 0, and 0 0 0. So at 8 clock cycle it will come to the initial state. Okay, so like this we can see in the EDA playground. And coming to the Vivado. So go to the design sources, add the design sources, next create the design sources. Give the module name only. What is my module name? Johnson counter. Copy this and give the module name. Choose the location where you want to store this code. Select OK. Finish. OK. Yes. This is my Johnson counter. So select all. Copy and here select all. Copy. Paste. Save. So I want to see the design. Right click. Set as top module. Okay. And next go to the simulation. Yeah, it made a top model. Add the simulation sources, create the simulation sources, give the test bench name. Okay, what is my test bench? This one. Copy this and paste over here. Choose the location. Special counter. Select OK. Finish. OK. Yes. TB. So Johnson counter underscore TB. Okay. Right click. Select all. Copy and paste. Save. If you want to see the simulation, right click set as top model. Okay. And I want to see the elaborated design. Go to RTL analysis and do the open elaborated design. Yeah, like this I can see the code is converted your code means the compiler is converted your code into gate level netlist. So as Q bar is connected through the inverter, okay, Q bar is connected. So Q is connected through the inverter is same as Q bar is connected as the input, no? So like this, okay, and a reset clock and four flip flops will be there. Okay, these are the four flip flops. Okay, and coming to the simulation, run behavioral simulation. Yeah, you can see in the simulation part, just fit to page, right click, give radix as a binary, and here you can see. So during when reset is activated, initially it is zero only. Okay, when reset is deactivated, you are getting this. Okay, so like this, so reset is deactivated, we are getting this. Okay, so 0001, 0011, and next during this passage 0111 and 1111 and 111110 and 1100, 1000. Again, at eighth clock cycle, it is coming to the initial state. Okay, so like this, we can see in the simulation part. Again, it will repeat. Okay, and next coming to the log file, you can see in the log file. See here. So when reset is activated, the output will be zero only. Output will be zero only. And when reset equal to zero, initial state is 000 and 0001, 011, 0111, four ones, and 1110, 1100, 1000. Again, it will is coming to the 000. Okay. Again, it is repeating. See here. At eighth clock pulse, it is repeating. Okay. So like this, we can see the waveform and the circuit in EDA play, Vivado, Xilinx Vivado. Okay, and quarter prime and model sim. So due to time being, I am not doing. If you want, I will share the code just to keep in the comment box. I'll share the codes and hope you install this quarters prime. Install the quarters prime light only. That is, if you install that, it will not ask for any certificate like license. Okay, model sim is anyway it's a open source from the Intel or yeah, you can install that model sim and you can see the waveform in model sim and you can see the same like this netlist you will get in the quarter spread. Okay, so with this we completed the day 13, that is special counters. We discussed the ring counter as well as Johnson counter. Okay, thank you.